It's very nice to be here. I feel back at home, even at CMU, even if this is just a virtual event, but I'm very comfortable here. And I'd like to begin by mentioning the SQL injection that the moderator said like, oh, we're still talking about this after all these decades, and it's a thing. We have to worry about things from the past, and we also have to worry about the new things that are coming, like quantum computing. This is gonna be a big thing, and it's gonna bring a lot of risks. So we have to be very careful. And we're gonna talk about the impact of quantum cryptography today. So what's the context of the problem? Today, we use asymmetric cryptography for many things. And we use algorithms such as RSA, El-Gamal, elliptic curve, and for example, Diffie-Hellman key exchange, which is not asymmetric cryptography, but it will be broken too. How does asymmetric cryptography work? We have the information here. This can be a message. This can be, for example, my name, Samuel. And if we want to encrypt it, we do it with a public key. This public key, as its name says, it's public. So you can encrypt the information with that. You send it all over the internet, and when the receiver receives it, he's gonna decrypt it, or she's gonna decrypt it with her private key, and she will obtain the original information. And this is the process. But turns out that quantum computing will be able to break this. Today, to implement this scheme, for example, if I want to communicate with all of you, what I do is generating a key pair. I generate a public key, a private key, and I send you all my public key. So when you want to write me, you will encrypt the information with the public key, and when I receive it, I'm Samuel, which I'm the only owner of the private key, and I'm the only one that has that private key. I'll be able to decrypt the information. But as I said, this will be compromised with quantum computing. All these algorithms are for that, and quantum computing can crack them. There's another scheme, which is called symmetric cryptography, and this will not be broken. We can use, for example, Rover quantum algorithm to attack it, and it can downgrade AES 256, which is a very famous algorithm. I mean, it's a standard. It literally is advanced encryption standard. This is the length of the key, is 256, and if you attack it with Rover algorithm, you can downgrade it to a key length of 128. But turns out this is still pretty secure, so there's no issues with this. Symmetric crypto is still safe. How does symmetric crypto work? You have the information, you have a secret key, which is the only key in this scheme. You use it to encrypt the information. You get something like this that no one understands. If a hacker gets this, or a thief, because there are many good hackers, like many friends I have from the INI, but if a cyber criminal steals this information, he won't be able to do anything with it because it's encrypted. And at the other end, you decrypt it with the same secret key, and you get, again, the original information. But this has a huge problem. Imagine that I'm here in Colombia, like I'm right now, and I want to send a message to a friend that is, I don't know, in Australia or China or Japan, at the other side of the world. I would need to send him the secret key in some way. So that's a big problem. I would have to take a plane, give him the key in a piece of paper, because if I send it through the internet, the attacker would be able to take the key and then decrypt the information. So I'm doing nothing. So today's schemes work in the following way. You use the public key to encrypt the secret key, and you send it encrypted with the public key, and when the receiver receives it, he decrypts it with the private key and gets the secret key, and then you begin to communicate with no problem. We do that because symmetric encryption, for example, this algorithm works much, much faster than any of this. And that's how we work today. But as I said, 3 times, this is in danger. It's going to be broken. Why? Because in quantum computing, we can tackle problems in a different way. The security of those algorithms, or at least RSA, relies, and that is very hard right now to factorize prime numbers. If you multiply a huge prime number by another huge prime number, you can do that very fast. But if you get the result and you tell someone, hey, tell me what are the factors? What were the two numbers that I used to get this big number? It's very hard. It's a very hard problem. And in traditional computing, we don't have an efficient way to factorize primes. Turns out that with quantum computing, we have two new properties. One of them is superposition, and the other is entanglement. Superposition is something crazy. Have you heard about the Schrodinger cat and things like that? It's all related to this. You can have, in a traditional computer, imagine you have a bit. That bit can be 1 or, or that bit can be 0. It can only be one of those two possibilities. It's binary, literally. But in a qubit, which is the counterpart of a bit, you can have a qubit in a superposition state. It can be 1 and 0 at the same time. And how it works is that, for example, you may have a qubit state that is 50% of being 1 and 85% of being 0. And the qubit state is like that, and you only can tell the value when you measure it. So at the end, you only see 1 or 0 when you measure it. But if you repeat the experiment many times, you will figure out these probabilities. For example, in the same way you throw a dice, and if you throw it many times, you will realize that, for example, 4 has 1/6 of probability or something like that. But that's a very interesting property that allows us to create many new algorithms, because you have a continuous value that can range from 0 to 1 in a single qubit. Other property is entanglement. In this, for example, in a traditional computer, you can have one bit that has the value of 1 and another bit that has the value of 0. And the value of 1, the value of this bit doesn't affect the value of this bit. They're not related in any way electronically. You can put 0 here or 1 and nothing bad happens. In qubits, you may have one qubit next to another qubit and they can become entangled. You can make them entangled, so the value of one qubit affects the value of other qubits, and that allows you to process exponentially more information. And I'm not trying to say here that quantum computing is more powerful, because let's see a simple example that makes it look really bad, and is that in quantum computing, you cannot copy-paste a qubit. This is a trivial operation in a traditional computer. You can copy one bit and replicate it any times you want. Turns out in quantum computing, if you have this state, you cannot copy-paste it. You cannot replicate that qubit, which is pretty lame. It makes things hard. So, for example, if you have, a service that if you want to send money to someone, they would subtract a number from your bank account and add it to other bank accounts. That's a simple operation that performs much better a traditional computer. So quantum computers are not better, they're just different. But since they're different, they can crack RSA. And some people are very optimistic about quantum computing. In fact, a group of Chinese researchers in December 22, they published a paper in which they claim they could crack RSA 2048. Remember, this is the key length. This is a strong version of RSA today. And they say we only need 372 qubits and a few thousand qubits of depth. So, like around 4,000. And some people, of course, were a skeptic. They say, no, I don't believe in that paper. They had some flaws, maybe. They didn't explain why the paper had flaws, but simply they say they didn't trust that result. So, of course, there are skeptics. Other people believe, no, this is a real threat. This is advancing really fast. And in fact, last year, the most powerful computer was an IBM, which had 128 qubits. Today, there's another IBM that has 433 qubits, which is called the IBM Osprey. So this is advancing fast. And IBM said that by 2025, they will be able to have a quantum computer with 4,000 qubits. And we have talked to IBM persons in our company, and they say, yeah, this is real. We're not telling lies to increase our stock market. This is really happening, and we should be scared. Of course, there are pessimistic people about the advancement of quantum computing. For example, the senior director of data and security research at Fujitsu said that their research demonstrated that quantum computing doesn't pose an immediate threat to existing cryptographic methods. But I read that article, and for example, they didn't mention alternative algorithms. They just tried to implement Shor's algorithms. By the way, Shor's algorithm is an algorithm that was invented in 1994, so that's a while ago, and it was made by the mathematician Peter Shor. And at that time, we didn't have quantum computers, but he said if we would have a quantum computer, we would be able to potentially crack RSA with this algorithm. The idea of quantum computers was actually, it comes from Feynman, which is a physicist, like from a while ago, and he made an adder, like a way to add like an adder in a calculator. He did it with quantum states. But the thing is, this has this flaw. I mean, this article, they didn't thought of newer alternative approaches. They also run the simulation in 39 qubits in a supercomputer. I mean, they were not real qubits, and we have real qubits today. We have a quantum computer that has 433 real qubits. They run a supercomputer that simulated 39 qubits, which is like, why did you do that? You could have partnered with IBM or with other big company that has real quantum computer to run your experiments. And also, probably you have seen many anecdotes of people predicting the future very wrong. I remember like 1 week before ChatGPT was released, there were people in the computer science field that said, oh no, it's gonna be a long while before we can talk to a chatbot that seems a bit humane, because you can always talk to a chatbot, and they had memes that artificial intelligence was actually a bunch of if clauses, like in programming. So if you say this, respond this, and things like that. So they thought it was not real intelligent. But when ChatGPT came out, we were all impressed. Even I worked with neural networks and deep learning and things like that, but I was impressed because it felt like another human. I mean, if the robot didn't tell me, hey, I'm a robot, I could have thought that it was a person. So this can suddenly improve a lot, and that can happen in any field, in any area of the computer science field. And he also said, not immediate, but how long? Turns out that how long is a very important question. Why? Because there's an attack called harvest now, decrypt later. You can capture in the network information today, and even if you cannot see it today, you may save it and try to decrypt it in 5 years. For example, the credit card expiration time can be from 3 years to 5 years generally, but there are credit cards that can expire or that can be useful for more than 10 years. So if I capture the network traffic today of some organization, for example, I put a sniffer in a point close to a bank, or even there's a conspiracy theories that ISPs, I mean, with ISPs, I mean internet service providers, that they store all the information from everyone, and even if it's encrypted, they save it just in case. So that can be happening today. And if, for example, the Chinese researchers are right, and in 4 years we can crack RSA, what's going to happen to all those credit cards? I have made a lot of purchases. They could see my credit card and make many frauds. Also, this is for credit cards, but imagine in clinical history, how long does that have to be protected? One would think a lifespan. For example, if I have an illness, I don't want everyone to know that I have that illness. That illness. For example, we have seen in the U.S. politics that people claims that some politician has some specific illness, and that makes him not fitted for the job or things like that. So of course, clinical history is something super important to keep confidential. Also, industrial secrets. How long do we need to protect an industrial secret? For example, the recipes of cookies or even sodas, Coca-Cola, Pepsi, all that. They have a recipe, and if it's leaked, it's going to be a problem. So you maybe need to protect it for a long while. Turns out that in military records in many countries, I say many countries because I don't have the data of a specific country. I have some friends that work at the Air Force, and when I ask them, what are you doing? How was your day at work? And they tell me, no, I was just gardening. They do everything, and they tell me, no, I was just gardening. They can't talk about their job. But in many documents, they say that top secret information must be protected for 40 years. And other fundamental topic is source code. When you're programming, you finish a nice piece of code and you push it into your repository. If you're developing software, you do that all the time. The source code travel, and if it's proprietary source code and it's stored by the ISP or by a cyber criminal, it will be stored and it can be decrypted in some years. And that depends on the company, how long you need to protect it. Some companies will say, no, the old versions, we just open source it or give them for free. Other companies say that, no, our products are undisclosed eternally. We don't want to share our code ever. So this is a real threat. Harvest now, decrypt later. So what can you do about that? NIST, which is the National Institute of Standards and Technology, has been working very hard in standardizing post-quantum cryptography algorithms. There are 3 for digital signatures, and there is 1 for public key encryption. They're in round 4, so they're not a standard yet. But we're mostly worried about this because of the attack I've been talking about, because digital signatures, I mean, they're of course something important, but for example, if I buy a house today and I send a digitally signed document saying that I want to buy that house, they give me that house, I live in that house for 4 years, in the records appeared that the signature at that time was valid and there was the technology available to forge that signature. So there are some attack scenarios, but they're not as critical as encryption. And turns out that all these algorithms can be run in traditional computers. You don't need a quantum computer to run it. In fact, some of them are based in ideas from the 70s, like ideas like learning with errors or things like that. And you can run them in your cell phone, in your laptop, in a mainframe on a bank. It doesn't matter. They can be run everywhere, but they're just not a standard. But there are several scenarios. In some scenarios, if you have custom software today and you're already worried about what you're sending through the network, you can apply these algorithms today. This is an example of a digital certificate, a real one. And we see here that it has a public key. This is, of course, an RSA key. A digital certificate is basically a public key, but with a bunch of information. It has the issuer, a valid from, a valid to, who's the subject, etc. So it's a public key with other information. We have here an RSA key of 248 bits. So that's what contains a digital certificate. But turns out that there are other fields that you can use to put additional information. So you can easily put a post-quantum key in another field. For example, this is just an experiment. but this is happening in real life. This is in use today for some very paranoid banks are using this. So they put a post-quantum key in another field. We can see it here. And they can use the public key, the RSA public key as usual, but they add another layer of security. So they encrypt with the RSA key, and they also encrypt with the post-quantum key. And in that way, they share information and they feel more secure. Other scenario, imagine when you're making a purchase and you put your credit card in a browser. The information travels from your browser that might be here in a laptop all through the internet until it reaches the server. So this information is generally protected with a protocol that is called TLS. But in the past, many banks implemented a second layer of encryption, not because of quantum computing, but because TLS had many vulnerabilities through history. And his predecessor, SSL, it was much worse. So here are some listed. It was Heartbleed. Maybe all of you heard about Heartbleed that appeared on the news and things like that. Then Poodle, in which you could downgrade the protocol to become SSL and apply a padding oracle, which is a very interesting attack that brute force a single byte at a time. And there were other attacks. So banks were okay. Our layer of encryption is gonna break. TLS is good, but it can break at any point. So we need to apply security in depth. In any information security area of an organization, they believe in this concept. Security in depth, which means you need to apply many controls to protect an asset. You don't leave it protected just by one guard, but you put many in different layers. So some people, some organizations said, okay, TLS can be broken, so we add a second layer of encryption with their own protocol, for example. So you can understand how roughly how this protocol works. You could put a second public key in the server that can be hard-coded in a JavaScript file. Since it is public, it doesn't matter. For example, it can be a post-quantum public key. When the user downloads it, that travels across the internet. Since it's public, it's not an issue. The user generates an AES 256 key, which we know is super strong, and use the quantum public key to encrypt this key and send it encrypted back to the server. And then now they have an AES key in both sides, and they can communicate and encrypt the information again, but with other different protocols. So they feel more secure in that way again. So this is when you're talking from the browser to the server. So that's how you can put a post-quantum layer to protect your information, and this is being done right now. It's easy. These two scenarios are easy things. When it becomes hard, when you're in DevOps, you have to push code all the time. So what can you do? For example, if you're using a third-party Git solution, or for example, like GitHub, you cannot tell GitHub, hey man, I want you to encrypt the information with this key with my protocol. No, you're just gonna use their platform. So what some people does is to keep everything in an internal network. So they don't send, of course, they don't use GitHub, they have their own repository, and they keep everything they have in an internal network. This scenario is unlikely post-pandemic because even radical companies allow their employees to go once a week to work from home, to go to their home once a week, and they work there, and maybe some developer finished a piece of code and he wants to push it. So this is not a great idea, but for example, I'm sure in the military, they do everything like that. Of course, employees are not able to take the source code of a nuclear weapon to their house. I bet they have everything inside an internal network. Other scenario, but okay, this can work in some scenarios, it's what I'm saying. Other scenario is that if your binaries are public but not obfuscated binaries, you can push obfuscated code. So in your build, for example, in your Gradle or in your Maven, you can have a task that encrypts the code at the end after compiling and all that, and push and encrypts the source code to push it to the repository. And you also push the mapping. What is the mapping? It's a file that maps the original source code, which has the original variable names and things like that, to the obfuscated source code. So you push that encrypted file. Of course, you have to share this AES key with the developers through other channel that is not the internet. You share that and you push that file, but beware that obfuscation can be reversed. In fact, at CMU, there's a course called Reverse Engineering, in which they give you a super obfuscated malware, and you have to reverse it and understand everything that it does. So this case, I don't think it's very interesting, because if you have public obfuscated binaries, you don't have secret code. I mean, you shouldn't be too worried. Another scenario that is more useful is that you push your source code encrypted with an AES key that you shared previously with every developer. But this is kind of very inconvenient. It's an ugly scheme, because you need to put manually the AES key in the server and locally. That makes it boring. And also, you wouldn't be able to use in browser features, like, for example, in GitHub, you can see what changed in the source code and things like that. Or even if you use GitHub, you couldn't use this strategy, because that violates their terms. They say that you cannot push encrypted source code. So you have to have your own repository, and it's an uncomfortable solution. But even if it's uncomfortable, maybe it's necessary, because, as I said before, there are optimistic or pessimistic views, but in cybersecurity, we're neither of those. We're paranoid. In fact, paranoia is our profession. This is a saying that comes from the CIA or maybe the KGB. It's an old saying, but it applies perfectly to us. So we shouldn't take our chances and hope that quantum computing doesn't advance. So if you're a normal company, you maybe are good if you wait. So Crystal Kyber is approved by NIST, is currently in Route 4. So, but as soon as it is approved, implement it. Don't wait like some people that still uses. I mean, you can find online that they still sell SSL certificates. This is broken a decade ago. It is far broken, and people, they still sell it, and some people buy it and don't understand the problem. So as soon as NIST approves this, you have to implement it. Of course, if you're working with very sensitive information from some super secret thing in the government, maybe you would have to use one of the previous strategies. And as we saw, in Git, third-party solutions can be uncomfortable. But if you have your own apps, for example, to secure the communication between client to browser, it's kind of easy. And remember, it's better to err on the side of caution than telling your CEO, "Oh, all of our information is compromised because I thought quantum computing was not going to advance this fast," because it's advancing pretty fast, and we should be worrying about this today. And that's all. Thank you very much.